Hi guys, welcome to Chemistry 24/7 series. Today we are going to see interesting problem which is based on asymmetric synthesis. So this is the question from CSIR 2011 December. According to this question, cyclohexanone which it react with this compound. This one is hydrogen derivative, then followed by react with LDA and methyl iodide that produce compound A, which further undergo ozonolysis that provide compound B. So let's break down this problem step by step in our this slide. So now you see here you see cyclohexanone which it react with this chiral auxiliary. I hope most of them aware about chiral auxiliary which is highly useful in asymmetric synthesis. So this is one of the chiral auxiliary. That chiral auxiliary name is SAMP. Here SAMP indicates that S means that configuration of this center. Then AMP means that amino methoxypyrrolidine. So when you react with cyclohexanone with SAM, that readily provide corresponding hydrazone derivative. So this hydrazone derivative further react with LDA under minus 78 degrees Celsius that quickly provide corresponding aza-enolate. So here you see aza-enolate ion. For better understanding, we can redraw this structure into their corresponding constant state model. So this will help us to visualize how this reaction is occurred by stereoselectively. So now you consider this part is R1 and this part is R2. Based on that one, you just rename as R1 and R2. After that, we should keep in our mind some important points. The first point is this carbon-carbon bond should be present in E configuration, and similarly this carbon-nitrogen bond should be present in the Z configuration. Okay, so now you see in this structure this nitrogen-nitrogen bond is rotatable. Therefore, if you rotate like this, so you will get this conformation. However, the configuration of this center is not changed. So now you see this CH2 OMe group, this methoxy group coordinate with lithium, and simultaneously two solvent molecule also coordinate with lithium. So this whole form present in the plane of the slide. However, the top face is highly sterically crowded by these two methylene group. Now you compare with bottom face is slightly less sterically crowded. Therefore, it is really difficult to approach the methyl iodide from top face while the bottom face is free. Therefore, our methyl iodide will approach from bottom face, then followed by this enolate, attack the methyl iodide by pack side to yield this corresponding product. So up to this step, this reaction is called as SAMP alkylation. The next step, when you do ozonolysis, you will get the corresponding ketone product. So the ozonolysis of hydrazone somewhat similar to ozonolysis of alkene. However, the mechanism is totally different from alkene ozonolysis. So next slide, we'll see how this ozonolysis occurred. So initially this hydrazone react with ozone by 3+2 cycloaddition reaction to yield this corresponding ozonide intermediate. Now you see this nitrogen lone pair of electrons shifted towards here, then followed by this nitrogen oxygen bond cleave to yield this type of intermediate. This ozonide intermediate as well as this intermediate both are present in the equilibrium. So now you see this electrons comes here, then followed by this electron shifted here, then this carbon nitrogen bond cleave to yield the oxygen gas as well as a ketone product, and this product also, this intermediate also. Now this intermediate once again react with ozonolysis that yield oxygen as well as nitrosoamine as a byproduct. So this product we can quickly convert into the corresponding ZAMP by the treatment of zinc acetic acid. So based on our discussion, we can easily pick the correct answer from these four options. Here you see the A is the correct option for this particular question.